In this video, we will explore searching algorithms. Searching algorithms are efficient ways to find elements in collections. Let's begin with linear search. Linear search sequentially checks each element in an array until the target element is found or the end of the array is reached. This algorithm works on unsorted arrays, making it versatile for various datasets. Its implementation is straightforward, making it easy to understand and apply. However, it is less efficient for large datasets due to its time complexity. Here is the time and space complexity for the linear search algorithm. Best case is order of 1. Average case is order of n. Worst case is order of n. Space complexity is order of 1. Here is the sample code for linear search in Python. We define a function called linear search, which takes an array and a target value as input. The code iterates through each element of the array. It checks if the current element matches the target. If a match is found, the index of the element is returned. If the target element is not found in the array, the function returns -1. Let's visualize how linear search works. We have an array to search. The target value is 7. The linear search process involves the following steps. First, compare the element at index 0, which is 5, with the target 7 not found. Next, compare the element at index 1, which is 2, with the target 7 again not found. Then compare the element at index 2, which is 9, with the target 7 not found. After that, compare the element at index 3, which is 1, with the target 7 still not found. Finally, compare the element at index 4, which is 7, with the target 7, and we found it. Therefore, the target is found. Next, let's delve into binary search. Binary search is a divide-and-conquer approach, which makes it highly efficient. However, it requires the array to be sorted. This algorithm works by repeatedly dividing the search interval in half. If the middle element matches the target value, the search is successful. If the target value is less than the middle element, the search continues in the left half of the array. Otherwise, the search continues in the right half. This process eliminates half of the remaining elements in each step, making it very fast for large datasets. Now let's look at the time and space complexity. Best case is order of 1. Average case is order of log n. Worst case is order of log n. Space complexity is order of 1. Here's the sample code for binary search in Python. We define a function called binary search, which takes a sorted array and a target value as input. We define the search boundaries left and right. While the left boundary is less than or equal to the right boundary, the code finds the middle element. If the middle element is equal to the target element, return the middle index. If the middle element is less than the target, search the right half. Otherwise, search the left half. If the target element is not found in the array, the function returns -1. Let's visualize how binary search works. Here's a sorted array to search. The target value is 11. The binary search process includes these steps. First, initialize left equals 0, right equals 6, and calculate the middle as 0 plus 6 divided by 2, which equals 3. Next, compare the element at index 3, which is 7, with the target 11. Since 7 is less than 11, search in the right half and set left equals mid plus 1, which equals 4. Calculate the new middle as 4 plus 6 divided by 2, which equals 5. Compare the element at index 5, which is 11, with the target 11. Since 11 equals 11, the target is found at index 5. Now let's compare binary search with linear search. Linear search works with any array, whether sorted or unsorted. It checks elements sequentially from start to end. Its time complexity is order of n, which is linear time, and its space complexity is order of 1, which is constant space. It is best suited for small datasets, unsorted arrays, and one-time searches. In contrast, binary search works with sorted arrays only. It divides the search area in half each iteration. Its time complexity is order of log n, which is logarithmic time, And its space complexity is order of 1, which is constant space for the iterative version. It is ideal for large sorted datasets and repeated searches. Let's discuss interpolation search. Interpolation search is a position-based search algorithm that requires a sorted array. It works best with uniformly distributed data. This algorithm uses a value-based formula to guess the position of the target element. Here's the time and space complexity. Best case is order of 1. Average case is order of log n. Worst case is order of n. Space complexity is order of 1. Here is the sample code for interpolation search in Python. We define a function called interpolation search, which takes an array and a target value as input. The code calculates the position using a formula. If the element at that position is equal to the target, the code returns that position. If the element at that position is less than the target, the code updates low to position +1. Otherwise, the code updates high to position -1. If the target element is not found, the function returns -1. Let's visualize interpolation search. Here's a uniformly distributed sorted array. We're searching for the value 40. The interpolation formula is as follows. Position equals low plus target minus array at low times high minus low divided by array at high minus array at low. This formula estimates the likely position of the target value, based on its value relative to the lowest and highest values in the current search range. The steps to search for value 40 are: first, initialize low equals 0 and high equals 6. Next, calculate the position using the formula. Position equals 0 plus 40 minus 10 times 6 minus 0 divided by 70 minus 10, which equals 3. Then, compare array at 3, which is 40, with target 40. We found it at index 3. Now let's compare the different search algorithms. In terms of time complexity, linear search has an average and worst case of order of n. Binary search has an average and worst case of order of log n. Interpolation search has an average case of order of log n, but a worst case of order of n. Linear search can work with any array, sorted or unsorted. Binary search requires a sorted array. Interpolation search requires a sorted, uniformly distributed array. Linear search has a very simple implementation. Binary search has a simple implementation. Interpolation search has a moderate implementation. Linear search is best used for small datasets and unsorted data. Binary search is best used for large sorted datasets. Interpolation search is best used for large, sorted, uniformly distributed data. When to use each algorithm? Linear search is best for small arrays, or when the array is unsorted and sorting would be more expensive than searching. Use when simplicity is preferred over efficiency. Binary search is ideal for large sorted arrays where we need repeated lookups and don't know the distribution. It is the most versatile and reliable of the three algorithms. Interpolation search is most efficient for sorted arrays with uniform distribution of values, like phone books or dictionaries. Use when you know data distribution is uniform. Here are the key takeaways. Linear search is simple and works on any array, but it is inefficient for large datasets with order of n complexity. Binary search requires a sorted array but is highly efficient with order of log n complexity, dividing the search space in half each time. Interpolation search excels with uniform data distribution, achieving order of log n average case, but requires a sorted array. Choose an algorithm based on data characteristics, size, and sorting status for optimal performance. This chart compares the complexity of the three search algorithms. The x-axis represents the input size, and the y-axis represents time. The orange line is linear, which is order of n. The blue line is binary, which is order of log n. The green line is interpolation, which is order of log n. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.